Today, the topic of discussion is on basic concept of refrigeration and air conditioning. That is Module 3, Part 1, PEME 601B. Myself, Dr. Suman Das, HOD, Department of Mechanical Engineering, Swami Vivekananda Institute of Science and Technology. In this video, I will discuss air refrigeration system, Bell-Coleman Refrigerator, COP determination, actual air refrigeration cycle. Now, air refrigeration cycles. So now I will discuss the difference between heat engine, refrigerator and heat pump. Now, what is heat engine? Heat engine is a device which convert heat energy into mechanical work. Here, the high temperature, that is temperature T2, and the lower temperature, that is T1. So heat is coming from higher temperature T2, that is Q1, Q2 amount of heat is coming from T2, and that is rejecting Q1 at temperature T1, that is T1 greater than T2. T1 is always greater than T ambient, and uh, so the amount of heat that is converting into work, so that is the W. So W is the amount of work done by the system. So heat engine is nothing but a device which convert heat to work. Similar here, that is the refrigerator. So refrigerator is nothing but a device which converting, that is which supplying heat from lower temperature reservoir to the higher temperature reservoir, and some external work is to be applied on the device to achieve this. So here W are the refrigerator work, that means work is supplied to the refrigerator, to the device, and heat is coming from the lower temperature cold body to the higher temperature body. That is Q1 amount of heat is coming from the cold body, and that is entering into the hot body, that is the Q2. So Q2 is nothing but Q1 plus WR. So here T1 is less than the ambient temperature. Now heat pump. Heat pump is generally used in the cold country where the atmospheric temperature is very low. So that is the hot body. That means the heat is entering into the hot body and the from the cold body. So cold body maintain a temperature T1, but heat is coming from the cold body to the hot body. So some external work is applied on the system to achieve this. So this is the difference between a heat engine, refrigerator, and as well as the heat pump. Now the performance of a heat engine. So we know that the efficiency in case of heat engine, the term comes, it is the eta efficiency, that work done by heat supplied, work done, that is WE, heat supplied, that is Q2. So Q2 minus Q1 by Q2. Now the coefficient of performance of a refrigerator. So in case of refrigerator, the term comes, that is the COP, that is coefficient of performance instead of the efficiency of instead of efficiency. So COP-R is nothing but Q1 by WR, that is desired effect by work input. So desired effect is Q1 and work input is Q2 minus Q1. So the coefficient of performance of or energy performance ratio of a heat pump. So this is also nothing but COP or COPP. So that is Q2 by WP, that is Q2 by Q2 minus Q1. Here, so the sum of that means the COP of heat pump is nothing but the COP of refrigerator plus 1. If we add 1 in the COP of refrigerator, so you will get the COP of heat pump. So COP of heat pump is always greater than 1. So finally, COP of heat pump is nothing but COP of refrigerator plus 1. Now, open air refrigeration cycle. So in an open air refrigeration cycle, the air is directly, that means the atmospheric air that is present in the atmosphere, that is the atmospheric pressured air, led to the space to be cooled. That means the space that is to be cooled, so that air is supplied to that. That is called refrigerator. The air is then allowed to circulate through the cooler and return to the compressor to start another cycle. That means here air is the refrigerator. Air is a working fluid. This requires size of a compressor and expander to be large. So in the case of open air refrigeration cycle, so size of the compressor and also the expander be very large. The moisture is regularly carried away to the by the air circulated through the refrigerator. In the case of closed or dense air refrigeration cycle, in a closed air refrigeration cycle, the air is passed through the pipes and component parts of the system at all times. So the air is used for absorbing heat from the other fluid, that is called the brain, which is circulated into the space to be cooled. That means that air is circulated the space to be cooled. The air does not come to contact directly with the space. That means that air will not come directly with the space to be cooled. This system has the following advantage over the open air cycle. Now I will just discuss or show the advantages. Number one advantage. The suction pressure is higher than that of atmospheric pressure. Therefore, the volume of air handled by the compressor and expander is smaller. That means in the case of closed air or dense air, in the suction pressure is very high. That's why the volume handled should be less. In the case of compressor and as well as expander, both the cases. Number two, the operating pressure ratio can be reduced, which result in higher coefficient of performance. In this case, we will get high COP compared to the open air system. A reversed, so this is the air refrigeration cycle working on reverse Carnot cycle. So I will just show you that. Uh, just a minute. Yes. So a reverse Carnot cycle using air as a working medium is shown in the figure PV and TS diagram. So this is the PV diagram and this is the TS diagram. The reverse Carnot cycle is represented by the four processes as described below. Now, process number one. Process 1 to 2. If you see this is 1 and this is 2, that is called the isentropic compression. So all of you know that what is isentropic compression? That is reversible adiabatic. So during this process, the pressure of air increases from P1 to P2. So from the diagram, you see that due to compression, this is the pressure P1 and this is the pressure P2. Okay. Specific volume decreases from V1 to V2. So that's why the specific volume here initially that is V1 and after that will be V2. So volume will be decreased from V1 to V2. And temperature increases from T1 to T2. If you see the diagram, so the temperature that is T1. So that temperature is T1 and that temperature is T2. So T1 should be increased from 1 to 2, from T1 to T2. No heat is absorbed or rejected by the air during this process. So this is the reversible adiabatic. That's why asymptotic compression. So no heat is rejected or absorbed. Now the process 2 to 3, that is isothermal compression. So if you see the 2 to 3 from the diagram, during this process the pressure of air increases from P2 to P3. So P2 to P2 and this is P3. Specific volume decreases from V1, V2 to V3. So this is the V2 and this is V2 and this is V3. So specific volume should be decreased. From this diagram it is clear. Temperature remain constant T2 to 3. So if you go to a temperature diagram, so temperature remain constant. 2 to 3 should be remain constant. Heat rejected by the air per kg of air, that is Q23. So if you see the diagram, that is Q23. So that is the heat rejected Q23 area. So 2, 3, 3 dash. So this is the 3 dash, 3 dash, and that is the 2 dash. So this is the 3 dash and this is the 2 dash. So this is the heat rejected, this area. So that is nothing but T3 into, that is the temperature T3 into, that is the difference of the entropy, S2 minus S3, S2, so this is S2 and this is S3. Okay, so that is very clear. So this can be written, and that is nothing but, because T2 equals to T3, so this can also be written in this form, T2 into S2 minus S3. Now the next process, that is process 3-4 and process 4-1. If you see the diagram, and from the diagram it is also clear that process 2-3, that is isentropic expansion, same thing. In the case of isentropic expansion, during this process the pressure of the air decreases from P2 to P4. So during this process the pressure is decreases. So here the pressure was P3, and after that, after expansion, the pressure should be P4. Specific volume increases from V3 to V4. So this is the V3, and this is the V4. And temperature decreases T3 to T4. So this is T3, and this is the T3, and this is the T4. The temperature should be decreased. No heat is absorbed or rejected by the air. So here there is no heat interaction takes place. Next, process 4, that is point 4, process 4-1. So this is the process 4-1. Okay, so this is process 4-1, and during this process the pressure of air decreases from P4 to P1, and specific volume increases from V4 to V3. So the temperature remain constant. So here the T4 equals to T1. So T4 equals to, so here the T4 equals to T1. The temperature remain constant. Okay. So this is there are 4 processes. Now, from this diagram, it is clear that from this discussion, it is also clear that heat absorbed by the air, that is Q41, that is the area under this curve area, and this is the, that is T4 into S1 minus S4. So T4 into S2 minus S3. Similarly, work done during the cycle process. So W cycle, all of you know that. So that is the Q23 minus Q41, that is area under this curve. So finally we are getting W cycle is nothing but T2 minus T1 into S2 minus S3. Now the coefficient of performance. So coefficient of performance, that is nothing but heat absorbed by work done. So that is Q41 by W cycle. Put the value Q41, and that is the W cycle. And finally we are getting T1 by T2 minus T1. So T1 by T2 minus T1, these two will be cancelled out, and this is the coefficient of performance of the refrigeration system. Now, temperature limitation of reverse Carnot cycle. So, this is the temperature limitation of reverse Carnot cycle. For a reverse Carnot cycle, we know that T1 by T2 minus T1, where T1 is the lower temperature and T2 is the higher temperature. The coefficient of performance of a reverse Carnot cycle may be improved by the following methods. Number 1, decreasing the higher temperature T2 of the hot body, okay, and number 1 is this, and number 2 is the increasing the lower temperature T1 of the cold body. That means we can decrease the higher temperature to increase the coefficient of performance, or we can increase the lower temperature T1 of the cold body to increase the coefficient of performance. That means we can change the coefficient of performance to obtain the maximum possible CFP in any application. So this is the cold body temperature T1 should be as high as possible, and the hot body temperature T2 should be as low as possible. That means hot body temperature should be as low, and cold body temperature is as high. That, so if we just if we do this, we can increase the coefficient of performance. We can improve the coefficient of performance of this cycle. Now, vapor as a refrigerant in reversed Carnot cycle. So the reverse Carnot cycle can be made almost practical by operating in the liquid vapor region of a pure substance as shown in the figure TS diagram. So process 1 to 2 isentropic compression already mentioned in the diagram. What is the isentropic compression? The vapor during the compression or wet becomes dry saturated at the end of the process. Such a process is called wet compression. The temperature rise from T1 to T2. Compression work, that is W12, that is H1, H2 minus H1. So process 2, 3, that is the condenser process. So the condenser in the condenser process, during this process the temperature remain constant because at constant temperature the that is the condensation takes place. That means just change the phase. Heat is rejected from H2 to H3 and the refrigerant gets converted to liquid at the end of the process. So initially the refrigerant that is entering, that is in the form of vapor, and when that is released from the condenser, that is in the form of liquid. So Q223, that should be the heat rejected. It is nothing but the change in or difference of the enthalpies. So it is like this. So H2 minus H3. Now process 3-4. So this is the 3-4 process, isentropic expansion 3-4. So during this process, the flushing of the liquid refrigerant takes place with the constant temperature drop from T2 to T1, T2 to T2 to T1, the constant temperature drop. So this is the T2 and this is the T1. The refrigerant becomes wet at the end of the expansion. So this at the end of the expansion, so that is the temperature refrigerant become wet. So work of expansion, that is W34. So 34 that is H3 minus H4, that is the isentropic expansion. So in the isentropic expansion, that is the refrigerant becomes wet. So that is entering into the wet region. So this is inside the liquid plus vapor region. That means it is somewhat some part of the liquid, some part of the refrigerant is in the liquid form. So that is the mixture of liquid and vapor. That's why it is refrigerant becomes wet at the end of expansion process. So work of expansion is nothing but W34 is H3 minus H4. So this is the reverse Carnot cycle with the refrigerant. Now the process 4-1, the last process. So that is the during this process, the wet refrigerant evaporates, heat is absorbed from the medium, and refrigerating effect is produced. So this is called refrigerating effect. So 4-1. So we just, this is the evaporation process. So heat is absorbed here, and the refrigerant is converted into vapor, and that is this is the process 4-1. That is called evaporation process. So heat absorbed Q41 is H1 minus H4. So W net is nothing but that is the net work W12 minus W34. So we just put this value, that is a two enthalpy difference. So finally we are getting this. So COP of the cooling, that is the refrigerating effect by net work. So this is the refrigerating effect H1 minus H4, and this is the net work. So finally we are getting in terms of enthalpy. So this is COP of cooling is nothing but this. Now let us discuss with the help of example a problem. A Carnot refrigerator has working temperature, that is minus 30 and 35. It operates R12 refrigerant as a working substance. Calculate the work of isentropic compression, isentropic expansion, refrigerating effect, COP of the cycle per kg of refrigerant. If the actual COP is 80% of the maximum, calculate the power consumption and heat rejected to the surrounding per the ton of refrigeration. Now this is the given value. T1 the temperature is given, that is minus 30, T2 that is 35, refrigerant that is R12, COP actual is the 80% of the maximum COP. So from the table of the property chart, so if you just have to go to the table of the property chart, and so that value we get from the R12 refrigerant property chart. So these are the values. So in enthalpy that is entropy. Sorry, entropy is nothing but S1 equals to S2 is this. So if you see this diagram, the diagram is comparatively little bit smaller. So 1 to 2 is that is entropy is constant. So we are getting from that property diagram. Similarly, S3 equals to S4 is this H2, that is enthalpy at state point 2, and H2 and H3 equals to enthalpy at state point 3. These are we are getting from that property chart, that is the R112 chart. And F4, that is SF4 is this point, SF4 is this point, and SG1 equals to SG4, SG1 equals to SG4, so this is G4, and SG1, this is SG1, and this is HF1 equals to HF4, so HF1, so this point on 1, HF1, and this is HF4, this is the HF4, okay. And these are the values that is we are getting from the chart. So this is the formula, standard formula in the so S1, if we want to know the value of S1, so this is the S1 is nothing but the entropy at state point 1. So this is the one entropy at state point 1 we have to know. So entropy at state point 1 is nothing but SF1, that is F for fluid. So let's entropy at in the terms of fluid here, plus in x1 into, that means entropy Dynamis fraction at state point 1 into SG1 minus SF1. So that is the G means gas. So gas minus fluid. So how will you get SG1? SG1 means at just point is here on this, that is called G. That means on the gas line, that is the vapor line. And SF1, that means this one. This one is the fluid line, F for fluid. So just put this value and we are getting this S1. And x1 s1 and x1 s1 is known, s1 is known here, because s1 equals to s2, s1 equals to s2. So from this we are getting the value of the dryness fraction, that means how much the refrigerant is dry. Similarly, h1 we are getting the same formula fashion, and we are getting the value of h1. Similarly, s4, same formula fashion, we are getting the value of s4. And x4, that is x4 is nothing but, that is dryness fraction at state point 4 is nothing but 0.3218. That means 32% dry. It means maximum is wet in this case. Similarly, H4, we are getting the value of H4 in the same fashion. So work of compression is nothing but, that is the W12 equals to H2 minus H1. So W12, that is H2 minus H1, H2 minus H1, and work of expansion, that is work of expansion is nothing but W34 is 3 minus H4, H3 minus H4 is this. And refrigerating effect, Q41, that is H1 minus H4, H1 minus H4, that is equals to this. Heat rejected, Q23, that is H2 minus H3, is nothing but this. Just put the value H2 and H3, we are getting value of heat rejected Q23, that is heat is rejected. And work done, net work done, W12 minus W34, W12 minus W34, so this is the value. So COP cooling, that is Q41 divided by W net. So putting the value of this and W net work done, we are getting this value COP in terms of temperature. So T1 we know, T2 know. So we just putting this value T1 and T2, and we are getting the value of COP in terms of temperature, in terms of this formula. So the actual COP is 80% of the ideal COP, maximum COP. So we just multiplied the 0.8 and we are getting 2.99. So power consumption per ton of refrigeration. So this the 3.519 5167 divided by 2.99, that is the kilowatt. And the heat rejected per ton of refrigeration to the surrounding, that is 3.51. So if we just add these two, that should be the heat rejected. Thank you very much.